Assalamu alaikum wa rahmatullahi wa barakatuhu. I'm Bisma Parveez from International Islamic University, Malaysia, and today I'm going to talk about one of my work entitled Investigation of Morphology and Compressive Properties of Diamond Reinforced Porous Aluminium Composites. Porous aluminium composites are the lightweight materials that have exceptional physical, thermal, and mechanical properties. Because of their lightweight, excellent compressibility, high strength-to-weight ratio, these find applications as structural materials in aircraft and automotives. The porosities in these composites are achieved by means of foaming agents or space holders. Foaming agents such as titanium hydride, dolomite, and calcium carbonate are mostly used, and the space holders such as sodium chloride and carbamide particles are used. But there is some problem associated with these foaming agents and space holders. The decomposition of the foaming agents leaves some residue behind. This can deteriorate the property of the composites. Also, at times there is incomplete leaching of these space holders. To prevent all this, we are going to use the polymethyl methacrylate as space holder particles that have excellent formability, good biocompatibility, low decomposition temperature ranging from 360 to 400 degrees centigrade, and decompose completely, leaving no residue behind. Researchers have used many reinforcements in order to strengthen the composites like alumina, boron carbide, silicon carbide, and carbon nanotubes. But in this study, we are going to use diamond particles as strengthening materials for porous aluminum composites. And we are going to study the microstructure, density, porosity, and compressive properties of these materials. As can be seen, the figure C shows the TGF analysis of the PMA particle, which shows the decomposition range. And the figure A shows the diamond particles, and B shows the PMMA, spherical PMMA particles. Now, materials and methods. The methodology followed for the fabrication of these composites is powder metallurgy technique using space holders, in which powders of different weight percentage were mixed together in two steps. In first step, the alloy matrix was mixed, and in other step, alloy matrix was mixed with reinforcement and the space holder particles. And then compaction was carried out at 250 megapascal, followed by the sintering at 580 degrees centigrade for 2 hours. But prior to sintering, the heating process was done at 450 degrees centigrade in order to decompose all the PMA particles in the composites and get the porous structure. Then it was validated for analysis. For the morphological analysis, if you can see the pore structure, it has the macropore structure that resembles the morphology of PMA particle size and shape. Also, there was the uniform distribution of the diamond particles as evident from 3E. But there was a poor wettability between the aluminium and diamond particles as evident from the pores available at the interface of diamond particles and aluminium. And there are spherical porosities, which helps in the homogeneous distribution of macropores throughout the composite and provides better pore conductivity. Now, the density and the porosity. The density has been seen increasing with increase in diamond percentage, while as the porosity decreases. As the porosity levels achieved indicates the complete removal of space holders, as we only have 30 weight percentage of space holders, but the porosity is still 26.2. It means that the higher content of diamond surrounds the PMA particles and led difficulty in the decomposition of these particles. Further, from the XRD analysis, we can see the peaks of aluminium and the peaks of the diamond, and also some peaks of the aluminum carbide are also seen. It indicates that the reaction has occurred between aluminium and diamond particles during the sintering process. Further, the compressive properties were studied. From the stress strain diagram, we can see that it has three regions. One is the linear elastic region, where the cell wall bending takes place, and another is a plateau region where the cell wall bending continues, and it's that region where the stress remains constant while as the strain rate changes. And then there is a densification region where the cell walls collapse and there is a sudden increase in the compressive stress. The plateau stress and the energy absorption capacities of these composites has been observed to be increasing only up to 8% because of the presence of the denser walls with greater resistance to buckling and bending deformation. However, it decreased with increase in the content, and the relative density had significant impact on compressive properties. Further, the stress-strain curves also indicate the brittle behavior exhibiting severe variation during the plateau region. Thus, we concluded that the powder metallurgy technique allows formation of the homogeneous distribution of pores, macropores, and prevents the formation of the cracks. And also, the optimum porosity and density has been obtained at 88%, that's about 30.9%, and the density is 1.722. And the properties improved as a result of this good porous structure. Because of the addition of the diamond, the properties only improved up to 88%. Beyond that, it deteriorated. And there is somehow insufficient bonding at high content and also between the aluminum and diamond interface. Also, the XRD peaks reveal that main peaks intensities of all the samples decreased with increase in diamond content. So it reveals the ineffective sintering because of the presence of low wetting between the aluminum and the diamond particles. So this all can be improved by parameter optimization or varying the diamond size or coating the diamond. Thank you.